All right, guys. So before we get started, are there any questions on the homework so far? Questions on the homework assignment? Okay. The rest of chapter 6 is solving. The rest of chapter 6 is solving. Now, the first big property we're going to get with exponentials is, they call it the property of equality for exponential equations. I refer to this as the one-to-one property. One-to-one. And the big thing with this, focus up here, is that if the bases are the same, if both bases are the same, the only way that they could be equal is if the exponents are also. The only way that we can have, especially for this first problem here, 5 to the 3 minus 2x, guys. 5 to the 3 minus 2x equal 5 to the negative x, because both bases are 5. Both bases are 5. The only way I can put 5 to a power and have it equal 5 to a power is if both of those exponents are the same. That's the only way this works. So 5 to the 3 minus 2x equals 5 to the negative x. The only way we can have this be true is if 3 minus 2x is equal to negative x. The only way we can have this be true is if the exponents are the same. If the bases are the same, if the bases on either side are the same, and I will specify there only is one. We can only have one base on either side. The exponents have to be the same. So the only way 5 to the 3 minus 2x equals 5 to the negative x is if 3 minus 2x is equal to negative x. Now we need to solve. We need to get x by itself because there is no exponent with x. We don't have x squared, we don't have x cubed, we don't have x to the fourth. Since we just have x, we need to get it by itself. All right, guys. So the first thing we need to do is add 2x to both sides, because negative 2x plus 2x is 0, leaving us with 3 on the left-hand side. Negative 2x plus x, negative 1 plus 2 is 1x. X is by itself, so it tells us x is equal to 3. Questions on the first one? Questions on anything we've done so far? And if we wanted to check this, all we would need to do is replace x with 3. So if I wanted to check it, we would plug 3 into our 5 to the 3 minus 2x, giving us 5 to the 3 minus 2 times 3. And this should have the same value as 5 to the negative 3. At this point here, I just grab a calculator and say 5 to the 3 minus 2 times 3. And it tells me that it's 1 over 125. On the other side, we have 5 to the negative 3, which is also 1 over 125. So it's telling me that is the correct answer because both sides gave us the same value. Questions on this here? So x is 3. Now, especially on the ACT, because y'all are taking it tomorrow. Solving, the nice thing about ACT is it has 4 multiple choice answers. It told you to solve this. We could do exactly what we did here and we get the answer. Or I can pick one of those 4 values, plug it into both sides, replace every x with it. If it gives me the same value on both sides, it's the right answer. If it doesn't, it's not. We try a different one. We can go through all 4 choices and see which one's the correct answer, and that works for all solving problems. Any other questions on the first one? If we look at the second one, we have 6 to the negative 2a is equal to the 6 to the 2 minus 3a. Are the bases the same? Yeah, they're both 6, aren't they? And the only way I can have these two be equal and have the base of 6 is if their exponents, negative 2a, equaling 2 minus 3a. the only way I can have 6 to the negative 2a be equal to 6 to the 2 minus 3a is if their exponents negative 2a is equal to 2 minus 3a. Then what can we do first? We could add 2a or we can add 3a. I would add 3a. And the reason I would do that is because on the 2a side, we just have a. On the other side, we have the 2 and 3a. So adding 3a to negative 3a will cause this to become 0. But the right-hand side is just going to be now 2. Negative 2a plus 3a is a. So we get a equals 2. If we did add 2a to both sides, we would need to subtract 2 and then make sure a is positive. But either way, we should get that a is equal to 2. And we can check this here. We can go 6 to the negative 2 times 2 and get this here. And then we go 6 to the 2 minus 3 times 2. And even though it gave us a decimal, it gave us the exact same decimal for both sides. So that is the correct answer. Any questions on the first two? Three to the 2a equals 3 to the negative a. Do we have the same base on both sides? Do we have one base on both sides? Yes. So for this to be true, we know that 2a has to equal negative a. Only way this works. A is not to an exponent, so we just need to get it by itself. What can we do first? We can add a. We can subtract 2a. Either one works. Because if I add a to both sides, 2a plus a is 3a. A minus a is 0. Since there's nothing else left on the right-hand side, it just stays 0. And last but not least, we would divide both sides by 3, telling us a has to be 0. A is 0, and it feels like, does this work, does this not work? Well, we can check. 3 to the 2 times 0 is 1. The other side was 3 to the negative 0, which is still also 1. 1 equals 1. Both sides have the same value, so it works. And again, on the ACT tomorrow, if you come across an equation that is asking you to solve and you're not sure how to do it, start plugging those values into both sides. See which one gives you the exact same value on either side. Don't change it, don't modify it, just stick it in there. Questions on number 4 before we look at number 8? 2 to the 2x plus 2 is equal to 2 to the 3x. Since we have the same base on both sides and there's only one base, it means that 2x plus 2 has to equal 3x. If the bases are the same, the exponents have to be also. At this point here, we're just solving for x. We would subtract 2x from both sides. 2x minus 2x is 2. All right, guys. 3x minus 2x gives us x, telling us x is equal to 2. Questions on any of these so far? We ready for the next one? So number 9, we have 6 to the 3m times 6 to the negative m is equal to 6 to the negative 2m. Now this one here, we do see that all the bases are 6. On the right-hand side, we do have one base, but the left-hand side, we have 2. We need it to be 1 and 1. We can't have it set up in this way. But we do have one nice thing. When I multiply like bases, we add the exponents. So 6 to the 3m times 6 to the negative m is the same as 6 to the 3m plus negative m. When we multiply like bases, we can add the exponents. Well, 3m plus negative m is 2m. So really we're saying that 6 to the 2m is equal to 6 to the negative 2m. Questions on how we got here? Questions on any of this so far? If the bases are the same, and we have 1 on either side, the only way this works is that the exponents are equal also. So 2m has to equal negative 2m. And because we do not have exponents, we do not have m squared, m cubed, we can just get m's by themselves. We get them on the same side. And to do that here, I'm going to add 2m to both sides. 2m plus 2m is 4m. Negative 2m plus 2m is 0. So m is 0. We do need 1/6 on either side. So I couldn't have just gone straight from the starting problem, here to setting the exponents equal to each other, because I need one base on either side. I need 1/6 on either side. Does that make sense? So I can't just, for the next one, start off with negative 2x times x equals 1. I need the bases to be the same, and I have to have one of them. Because 13 has a few things going on. One, the left-hand side has two bases of 4. We need it to be 1. Now, luckily enough, properties of exponents say if I have two bases, or I have like bases being multiplied together, I can rewrite it as a single base with their exponents being added together. When we multiply like bases, we add their exponents. However, the right-hand side is not 4, it is 64. Yes. Now, knowing the problem, and because it's set up this way, we should expect 4 to have, or be written as 4 to a power to get to 64. Well, 4 squared is 16. What are we going to try next? 4. 4 to the third is indeed 64. Now we could, and I think this is what you might have been asking, I could drop straight down and say negative 2x plus x equals 3. Bases are the same, we have one of each, we can start solving. Or negative 2x plus x is negative x. So we can say 4 to the negative x is equal to 4 to the third. Well, again, the only way I can have like bases and these two be equal is if the exponents are equal as well. Does that make sense? So really we're saying that negative x is equal to 3. We can either multiply or divide by negative 1. Because negative x divided by negative 1 is positive x. Positive 3 divided by negative 1 is negative 3. 3 divided by 1 is 3. Positive divided by a negative is a negative. So we get x is equal to negative 3. Questions on any of this here? Questions on anything we've done so far? Interestingly enough, and we will get to this, you do not have to rewrite it. Truly, and realistically, what we're doing is applying log base 4 to both sides. Because as we talked earlier this week, when the base of the log and what's inside, the base inside the log are the same, it simplifies to what the exponent is. So log base 4 of 4 to the negative x is going to simplify to negative x. And log base 4 of 4 to the third is going to simplify to 3. That's really what we're doing on all these. You have this one-to-one property. Let's look at the next two. 100x equals 1/10 to the x minus 3. We're going to walk through it. We're going to work through it. But again, especially on the ACT, if you're not sure what to do, you have 4 answer choices. Start plugging them in. See which one makes both sides be the same. Now here, as we've been working with these last two, we want the bases to be the same, and we want one base on either side. 1/10 to the x minus 3. Well, it'd be nicer if it was 10 instead of 1/10, yes? We can get that, because if we move a number from the bottom of the fraction to the top, or top to the bottom, its exponent goes from positive to negative, or negative to positive. So when I move that 10 from the bottom of the fraction to the top, it goes from 10 to 10 to the negative first power. Because it is 10 to the first power on bottom, but its exponent becomes negative when we move it to the top. Now there might be a question, well, where did the one on top go? It's still there. We just have 1 times 10 to the negative first, but 1 times anything is just whatever we're multiplying it by. So we don't necessarily have to write in the fact that it's 1 times 10 to the negative first power. Questions on this here? This kind of helps us out. Since the base on the right-hand side is 10, we want the base on the left-hand side to also be 10. So 10 to what power is 100? Okay. So by doing this, have we made both of the bases be the same? Yeah. We're not so focused on what the exponents, signs, all that is. We need the bases to be the same. And we did that. We got both of them to be 10. Now, before we start setting exponents equal to each other, it might be helpful to simplify some of this out, because we do have powers of powers. And powers of powers multiply. So 10 squared to the x, 2 times x is 2x. And 10 to the negative first to the x minus 3, we're going to multiply x minus 3 by negative 1. Well, negative 1 times x is negative x. And negative 1 times negative 3 is plus 3. So we have 10 to the 2x is equal to 10 to the negative x plus 3. And since the bases are the same, the exponents have to be the same as well. First thing I would do is add x to both sides. 2x plus x is 3x. Negative x plus x cancels. Divide both sides by 3. X is equal to 1. And that's it. Questions on any of this here? Are we ready for the next one? Yes? (81 to the x is equal to 1/9 to the x plus 3. again, we want to rewrite these so that the bases are the same. What base are we most likely going to be using? Well, 9, because can we rewrite 81 as 9 to a power? Yeah, so it would be what? 9 squared, yes? Now, the reason I would pick 9 is because our other one, 1/9, would be 9 to the negative 1. We move it from the bottom of the fraction to the top, which makes that exponent go from positive to negative. Interestingly enough, if we wanted to, we don't have to, we could actually have set both of the bases to be 3. Because 9 is 3 squared, so 1/9 would actually be 3 to the negative second power. We could have used it. And 81 is actually 3 to the fourth. So it would give us the exact same solution. The values in the exponents would have been a little bit bigger. So on the left-hand side, our 9 squared to the x would be 9 to the 2x. On the right-hand side, we'd have 9 to the negative x minus 3. Questions on this here? Now, if we'd have used 3, we'd have had 4x instead of 2x, and we would have had negative 2x minus 6, but it still gives us the same value. Since the bases are the same, the exponents have to be the same as well. So for us here, we're saying that 2x is equal to negative x minus 3. Questions? Questions? Okay. All right. So at this point, we can add x to both sides. Negative x plus x would cancel. X plus 2x is going to be 3x. And last but not least, we would divide by 3. Telling us x is negative 1. The nice thing about exponentials or solving for x when x is in the exponent, the value of x can be any real number. Any real number. Logarithms, we do have restrictions, but if it's in the exponent, it can be any real number. This one's kind of nice. And I say that because the left-hand side has one term, its base is 3. That's as simplified as it gets. So for us to be able to use this one-to-one property, we need to figure out what 3 to what power makes it be 243. The 6. Fourth. Split the difference. 5, 243. So 3 to the 1 minus 2x is equal to 3 to the 5th. So we're able to get the bases to be the same. And once we get the bases to be the same, we can set the exponents equal to each other. What would we do first? Subtract 1, because x is already on the same side. We just need to get that constant term over to the other. Telling us that negative 2x is equal to 4, yes? Without doing anything else, we know that x is going to have to be, its value is going to be what? Negative, because the only way I can multiply a number by negative 2 and get a positive is if that value of x is negative, yes? So that means the two positive answers are gone. 4 divided by 2 is, so the answer has to be negative 2. And really, all of what I was saying and talking about there is We're seeing it, we're looking at it, we find the answer, especially on the ACT. Select that answer and move on. We don't have to write the whole steps out. As soon as we find the right answer, select it and move on. Seven to the 2x minus 3 is equal to 343 to the x plus 4. If we're going to be able to use one-to-one property, get these bases to be the same, 343 has to be able to be rewritten as 7 to a power. Otherwise, this doesn't work. So we can try 7 squared. 7 cubed is what we want. If 7 cubed didn't work, I would go to 7 to the 4th, 7 to the 5th. Keep increasing that exponent until we pass it up. Powers of powers. Multiply. 3 times x is 3x. 3 times 4 is 12. Since the bases are the same, the exponents have to be the same as well. So for us here, it's telling us that 2x plus 3 has to equal 3x plus 12. Now we just need to solve for x. Add minus 2x from both sides. Telling us that 3 is equal to x plus 12. No. Anybody see the issue? What is it?
It's 1x minus the 3 by itself because it's not its own power.
Yeah. Yeah, I put plus 3 instead of minus 3. Yep. So that should have been negative 15. And got negative x minus 3 equals 12. Negative x equals 15, yes. Yeah. Yeah. So your way works. It still gets to the same answer. Yeah. No, it's x equals negative 15. Mm-hmm. Yeah. Either way works. It just depends on how we move the first thing. Still gets to the same value. Still gets to the same solution. Are you ready for the next property? Property of equality for logarithms, still 1-to-1. If both logs, if we have one logarithm on either side, and it is the same logarithm put to the same base, what's inside has to be equal. So the only way the natural log of 4x minus 7 is equal to the natural log of x plus 5 is if 4x minus 7 is equal to x plus 5. This is the only way it works. Because we're applying the same function to both of them, so what's inside has to be the same. So the first thing we want to do, we need to get the x's on the same side. 4x minus x is 3x. Equal to 5. Then we can add 7 to both sides, telling us 3x is equal to 12. Divide by 3. Extend the page. x is equal to 4. Now, I want to say something in particular with logarithms. The variable that we're solving for can be negative, but when you plug it back in, if it makes the expression negative, it does not work. So what I'm saying is 4x minus 7 cannot be 0 or negative. If the value or the solution we get causes 4x minus 7 to be 0 or negative, or x plus 5 to be 0 or negative, that solution does not work. We cannot take the natural log of 0 or a negative number.
So if it was negative 4x minus 7 and x plus 5, it would not work whatsoever.
So it would work since the value of x is 4. Now, if I said that the value of x was 1, I'm going to erase this here. So if we solved it and said x is equal to 1, that's what we got. I plug it back in. By plugging it back in, 4 times 1 is 4. 4 minus 7 is negative 3. It does not work because I cannot take the natural log of a negative. I cannot take the natural log of 0 either. Natural log of 0 does not exist. Domain error. And that's the same for logarithm, any log. We cannot take a log of 0 or negative. Even if it told me, and I plugged it into both sides, it doesn't work here. It does, plugging in 1 into x plus 5 would not give me negative 3. But the point I'm trying to make is even if we plugged it into both sides and got the natural log of negative 3 is equal to the natural log of negative 3, it still does not work because we cannot take the natural log or take a log of a negative number. It doesn't matter that they both have the same number inside. I cannot take the natural log of a negative number. Not that we plugged in a negative, but when we plug it back in, I cannot take the natural log of a negative. Does that make sense? So if we look at this here, 7x minus 4, natural log of 7x minus 4 is equal to the natural log of 2x plus 11. For these two to be the same, it means that, make sure that doesn't look like 21, what's inside has to be the same as well. All right, guys. 7x minus 4 has to equal 2x plus 11 for these two logs to be equal. First thing we can do is 2x from both sides. 7x minus 2x is. So 5x minus 4 equals 11. Add 4 to both sides. 5x is equal to 15. And lastly, we need to divide by 5, yes. Because x is 3. I started writing the solution, not what we were supposed to be dividing by. But does this make sense? Yes? Questions on this here? Do you feel good with this so far? Because I don't think we need to do a lot more of these. I think we're starting to pick up on how this works, yes? Go to 11? Okay. Let's look at this one. Log base 12 of v squared plus 35 is equal to log base 12 of negative 12v minus 1. Again, like I said before, if you get a problem like this, solve the following logarithmic equation for v on the ACT. We have 4 answer choices, yes? Graphing calculator, log base, parentheses, plug that value of v in, pick one of them, and see which one makes both sides be the same. Now, we do have one log on either side, yes? Yep. We do have the same base on both sides, and they are the same logarithm, yes? So that tells us that v squared plus 35 has to equal negative 12v minus 1. Since they are the same log with the same base, both sides have to be what's inside has to be the same. Really what we're doing is putting both sides of this equation to the base of 12. Because log base b, so b to the log base b of x is x. It simplifies out. Because really what we're doing is applying both sides to the base of 12. Those are gone, leaving us with what's inside. Same thing. It's just a variable. Now, since we do have v squared, we have a variable to an exponent bigger than 1. We have to get this equation equal to 0. Now, the first thing, or one of the first things we can do is add 12v to both sides, or 12x. I'm going to switch it to x just so that we keep everything the same. X squared plus 12x plus 35 is equal to negative 1. Still not equal to 0, so the next thing we can do is add 1 to both sides. Telling us that x squared plus 12x plus 36 is equal to 0. Now at this point here, we can factor, we can graph, we can complete the square, we can use the quadratic formula. And especially on the test, on that ACT, I'm going to keep saying it, it's going to give us 4 answer choices, yes? If a radical, if a square root does not show up in one of the answers, we get x equals 1, 3, 5, and 6, it means that has to factor. It gives us integer solutions, it has to factor. Also, if it doesn't give us fractional choices, that means this thing can graph. We can graph it and see what values of x makes the y value be 0. If we factor it, since the third term is positive, the signs are the same and match the sign of the middle term, plus and plus. Factors of x squared, we only have one set, x and x. Factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6, 6 and 6. And if we did check it, it would indeed give us a middle term of 12x. Two things multiplied together equals 0. One of these has to be 0. We got 2 solutions. Realistically, we have 2 solutions. We have one unique solution because both of the solutions are negative 6. Still have 2 solutions, technically, and especially according to the fundamental theorem of algebra, but we only really have one unique solution. Yes? Questions on this here? Now, I did say that what's inside the logarithm cannot be negative or 0, yes? But here we got x to be negative 6. I'm going to erase this here. So if we plugged it back in, not what I wanted, log base 12 of negative 6 squared plus 35. Well, negative 6 squared, negative 6 times negative 6 is positive 36. And 36 plus 35 is going to be 71. What's inside the logarithm? Even though x was negative, what we have left is a positive number. We're taking log base 12 of 71. On the other side, log base 12, we'd have negative 12 times negative 6 minus 1. Well, negative 12 times negative 6 is positive 72. And 72 minus 1 is 71. So even though the value of x was negative, after we plugged it back in and simplified, what we had left inside the logarithm was positive. Do we see how that works? But that also means, especially when solving logarithms on the test, if you notice when plugging a value of x in, what's left over after simplifying what's inside the logarithm is negative, it doesn't work. We can throw it out. Questions on any of this here? That is it.